that you need to work on the mathematics that can lead somewhere and give you new tools to understand these problems. So sometimes you are in a completely dead alley, and what you do has no importance to anything anywhere. But sometimes you're not, and you have to go through dead alleys to find the right way. So Abala and I have done this before as well, and I always try to put a bit of myself in my talks, though not quite so explicitly usually. This time I'll be explicit and give you a bit of my life story. Like I said on the first day, you think everything is linear. You do your degree, then you do a PhD, then you get a postdoc, then you get a job, and so on. It's absolutely not linear. It's so full of troughs and moments of excitement, a lot of moments of despair. My particular path was very linear up to getting into graduate school at Yale, where I was with Mignon, by the way. We were very old friends. And then everything started getting its own shape. I stopped after starting my PhD. It's fair to say my chemistry with my supervisor wasn't perfect. And when I told him that I was expecting a child, he all but disconnected from me. He didn't think I would do anything. I did finally finish my PhD. Not, I mean, he did sign my thesis, but I worked with other people as well, and started working on PDEs that model wave phenomena. And particularly in those years, this was the late 80s, early 90s, solitons and solitary waves were very in vogue, and they had been first seen here in Edinburgh in the canal just right by Harriet Watt, so eventually I came back to them. But I worked on these kind of models, and waves that are close to solitons but not quite solitons, don't have all the properties and how exactly you can characterize them, and did a lot of numerics as well back then, because I wasn't sure I could get a job in academia after taking 10 years to finish my PhD. And so I thought, well, I better have some other soft skills if I don't find a job in academia. I need to find a job somewhere else. So I need to have something to sell. I'm not, it wasn't really my first love, it's fair to say, the computations and numerical work, but I did it. But then I was very lucky. I applied for one of these Marie Curie fellowships and got one to come to Imperial College to work there on a project that initially had to do with what I had done in my PhD, but then took a completely different turn. And that is very exciting about mathematics, keeping an open mind and not necessarily do what you said you would do, but follow some other lead. I was lucky because I arrived at a time when something was being started. So I got into this project of developing what is now known as the unified transform, which is really a sort of generalized Fourier transform method. It's a very general method to deal with boundary value problems. And I like generality. I don't like problems that have their own specific techniques. I like things that I can think you can apply to many different problems and have some sort of general principle that leads them. So I worked for many years on that. And both finding this problem and getting the fellowship really were a turning point in my career. Julia also spoke, or someone else spoke about fellowships. They are amazing if you can get one, because you are your own person. You can develop your own taste, your own project, but also they're very recognized. Of course, there are very few now, and they're not easy. When that ended, I didn't have a job. So at Imperial, the head of department then was very kind and sort of, they started doing a patchwork of funding to keep me on for another 2 years, I think, until I then got a job. Well, I wasn't looking for a job because I still had small children, and having not to teach suited me because it left me time to organize myself and work whenever I could. So I wasn't yet looking for a job, but then around 2000, I decided it was time to get a job, and I became a lecturer at the University of Reading, which was back then, well, I wanted to be close to London for personal reasons. Reading was in a fantastic place, very close to London, very close to Oxford, but everybody, when I went, there were maybe 2 people my age, I and a guy that was hired at the same time, and everybody else had been hired in the 60s and was on the way to retirement and was really quite dead. And I thought, everybody told me, don't go, it's a dead place. But in fact, there is something about going in a place like this. Everybody retired and there was a blank slate and it became a young department. We did, it certainly turned, and it was a very interesting place to be. And they treated me fantastically well. I really was happy there. I had time to settle the balance between my work and my life, and became reader as I was on my 4th maternity leave, and then professor, and then I started giving back, because I think at some point you also have to give something back. So I became head of department, half head of department. I said I would do it, but only with someone else in cooperation. And then I also developed the CDT, Mathematics for Planet Earth, that maybe Jennifer mentioned yesterday, possibly. She's there now. But I really, well, my husband is Scottish, but also we always came to Scotland. I love Scotland. I wanted to move here, so I started looking for opportunities, and I came in 2016 to become professor at Heriot-Watt. I really came as head of school, again, in a spirit of giving back to my community, because I did feel that the community had really helped me get to where I was. So I was head of school during COVID, and that was quite hard. But now I'm not anymore. And I have been very lucky to stumble onto a new problem that has taken my attention and kept me busy, and I will talk about that. And I also am currently not really doing anything more than helping Mignon here at ICMS. Mignon, Jane, and Gillian really should take all the credit. Okay, so let me say a bit about what I've done in general before I move to one problem. So I do like having some sort of general principle. I would say, in general, I've worked on boundary value problems, linear and nonlinear, mostly dispersive, because mostly these have been problems that come from fluid mechanics, water waves, or atmospheric fluids. And so they tend, well, they don't always are dispersive, but the kind of problems I've been looking at are dispersive. So the thing that I did that for the first 10, 15 years of my career, really, I concentrated on working on boundary value problems. Nonlinear, this is, if you know anything about nonlinear wave models, unidirectional, this is the linear part of the very famous equation, the Korteweg-de Vries equation. Korteweg-de Vries are the ones who tried to explain solitons that had been observed here in the canal. And so if you add the nonlinear term here, QQX, which is like the Burger's nonlinear term, that's Korteweg-de Vries, and you can show that it actually supports this special solution that are bumps that travel unaltered even when they interact. But that's if you assume, sort of the problem on the full real line, the Cauchy problem with nothing happening at infinity. In real life, there are boundaries usually, so it was important to try to understand what happens when you have boundaries and boundary conditions. And that was, to my surprise, even this linear problem was open. If you look in classical books, if you have the heat equation, 2-point boundary problem for the heat equation is in every book you probably study as an undergraduate. If you add one derivative, it's open season. Nothing was known really, or very little. Of course, when I spoke about this first in an integrable system conference, one Russian guy stood up and said that it was known in Russia, and it was published in Russian, but I didn't know about that. Maybe yes, maybe no, I'm not sure. Anyway, I studied this problem for quite a long time, and I'll say you a little bit more about it. And okay, so after a long time, I was in Reading, where there is a department of meteorology. I started looking for new things to do. And one thing that attracted me was working on a different type of nonlinear PDE, not 1D, 3D, which is a reduction of the full Navier-Stokes, but really Euler, because we discard the viscosity, thinking of the atmosphere, not really a viscous fluid. And the thing that attracted me is that there are some reductions that you can treat with this very general idea of optimal transport. Okay, and And even, and this is something I've pushed here with my PhD students, using this optimal transport approach to develop very powerful numerical models for this. And this reductions model flows over large range, so they are good for things like tropical cyclones, to model tropical cyclones or their path and things like this. And they are actually used as diagnostic tools in the big Met Office system. But what attracted me is the interplay between having some applicability and having some really general mathematics. This optimal transport is now, is in the last 15 years, has exploded as a really powerful variational tool in a lot of applications. And then what I will speak about today is something that is, I think, really beautiful, really unexpected, quite simple, but also with unexpectedly large implications, which is something that we call dispersive quantization or revivals. It was known for about 100 years as the Talbot effect, and it's something that unexpectedly happens when you look at linear problems that are periodic. And I will spend most of the time on showing you pictures about this. But I've pushed that away from periodicity, away from the classical Schrödinger equation that this was done on. Okay, so let me just give you the key words for this other three. So these are three classes of problems that I work on in my career. So the first one is this. So this is looks like a very tame problem. You're posing the simplest possible dispersive equation, linear, that there is in 1D, time and space, some initial condition. You can assume it any way you like. And then you just, this is third order, so you have to give three boundary conditions. And the first question is, if it's the heat equation, there is one at each end of the interval, but if it's three, where do you put two and where do you put one? Do you put all three on one side and so on? So even this wasn't known. How do you have to give the boundary condition to have a well-posed problem that has a unique solution? And it turns out that you have to give two on one side and one on the other, and which side depends on the sign in front of the third derivative term. And this can be classified in general for all orders. But what is more interesting is that, whereas for the heat equation, if you give the Dirichlet problem, I think, I haven't put it down, but you just write the sine series for the solution. Just Fourier series solve the problem. For this, you try to do Fourier series, and you cannot get rid of the three boundary conditions that you don't know. So there is the derivative and the second derivative, the derivative at one and the second derivative at both ends. So there are three unknown that come in when you just write down the solution for the Fourier transform of the equation, and you cannot get rid of them. The sine transform gets rid of the unknowns boundary conditions for the heat equation, but here you can't. And the way to represent the solution is not as a series, but it's as a complex contour integral, okay, which is not equivalent to a series representation. And that was quite a surprise. People didn't believe me when I started talking about this, but it's a theorem and it's absolutely true. It is not equivalent to a series representation because the eigenvalues behind the spectral structure of this problem are not real, they're complex. They are the solution of these transcendental equations. You cannot even solve it in closed form, though you can say where they are. And they're not on the lines where this discriminant delta is. Okay, so this is a well-defined complex contour representation. I won't go into the details, but it's just, this is the takeaway message. There are sometimes two boundary value problems, differential operators with boundaries that, although they are on a bounded domain, do not have a discrete spectrum, you know.
Could I ask some questions?
Sure. If you ask a question, I'll have to repeat it for the recording, but go ahead.
That.
Oh, sorry, Q should be you. Where have I left?
Cube term, lambda cube.
Oh, lambda cube.
But first is cube term.
From the third derivative. So take the Fourier transform of that, yeah, of the equation. Then you transform what is a PDE into an ODE. Yes, and each derivative gives you a lambda. So anyway, I haven't given you any details how you find this, but everything is explicit. This is a fully explicit solution representation, but it cannot be written as a series. And this has all sorts of ramifications also for CoEDV. Okay, second topic is this Fourier transform. This is work that my PhD students have done. So I should say I've sort of characterized this work with mentors. This is the stuff I started doing as a postdoc. And really, I had mentors in the sense that they were collaborators, but there was a sense of some hierarchy there. And so I've classified it as work with mentors. This has really been work with PhD students. And in fact, these cyclones, this is the evolution of a twin cyclone starting from some disturbance in the atmosphere. That's just the temperature, you can ignore it. These are the twin cyclones. These are particle methods. They're very, very expensive to run, but this optimal transport scheme runs it with 36,000 points or even 60,000+ points very efficiently in a very short time, and it's very accurate. It benchmarks against all of these things. But the point for me is that really it comes from this very general kind of formulation of the problem that allows you to use this very powerful optimal transport results. This is work of my current PhD student who is finishing this year, Theo, who is not here, but is around somewhere. Okay, so I was at this point, I had this kind of two things I was doing. And then as I was finishing my term as head of school, I was really looking, I was very nervous. Will I be, because while I was head of school, I had very little time for research. I had PhD students and I had a grant, so I had some postdocs, but they did the work. I felt I met with them, discussed, but I wasn't really putting my own thinking time into any of the things that they were doing. In fact, sometimes, and I think this is important too, because it's not common practice, but I didn't put my name on any of the papers because really I wasn't doing anything. And I was nervous finishing whether I would find something if I could think again and do anything. And so I went to a talk given by Peter Olver, maybe a couple of years before I finished as head of school. And in this talk, he's very good at giving talks that do not go in details, but give you the general idea. He said, okay, so I want to show you this problem. And as you will see, this is my lovely Airy equation, Stokes equation. It has many names, but it's an equation I knew intimately, okay? And he said, I'll solve the periodic problem for this. Periodic, it's easier because you just use the Fourier transform always, it's okay. And he said he was writing a book. It's a textbook on PDEs, and was trying to devise exercises for the book. And he wanted to give the following exercise. If my initial condition is not continuous, and it's a step function with a jump here and really a jump there too, because this is a periodic problem. So this is on the torus. These 2 points are identified. Can you write down the Fourier series for the solution? That was the exercise. And before actually publishing, he said, well, let me see what it looks like. And of course, you do it numerically. You just truncate the Fourier series and plot it. And if you do it at the times that it's normal to do it at, like you do it at, take a time step of 0.1, for example, these jumps gives a sort of super oscillatory solution, periodic. You can see that this is periodic. That's really enforced by the Fourier transform. But then, and I don't know why he did this, he looked at different times. Okay, he looked at times that are rational multiples of the period of this problem. This problem is on 0 to pi. And at this time, something completely different happens. In, the same initial condition, a step function, 2 jumps, 2 discontinuities. And at these rational times, these discontinuities are revived. They appear again, only at these rational times. And so this is a very pointwise phenomenon. In L2, you don't see any of this because rational times, they are measure 0 in the set of all times. And you don't see point discontinuities, there will always be some continuous function in the class. So it's not a sort of, and L2 is the space in which everybody does Fourier transforms, but this is a slightly different phenomenon, and it requires some attention. So he said, you write the solution as a Fourier series, it's not difficult to see why, but he had never seen anything like this. So this caught my attention too, because of the equation. I knew this equation, this is periodic, and I started thinking, what if it's not periodic? What if it's some other different boundary condition? And I got thinking about this problem. Let me just give you a bit of background on this problem, because in fact what Peter stumbled on, it's a very old, well-known thing that had been seen in optics 150 years ago or more, almost 200 years ago. Okay, this guy Talbot, who was one of these eccentric English polymath types, one of the first enthusiasts for photography. He was going around the English countryside taking photographs of lattice windows in the big abbeys and so on. And he noticed that if light passes through a window with a periodic type grating, this grating gets replicated, the image of the grating gets replicated at certain specific distances from the window. And he took photographs, and the oldest existing negative is his, for example. And he wrote about it many articles for the Royal Society and so on. And now it's known also as a quantum effect. It's really an effect of coherent interference in any of this kind of light propagation problem. So here is where the light enters through a periodic diffraction grating, and the grating is replicated here and then again there. And something like the grating has some replication at very different distances. Okay, so it's something that really happens. It's not just, this measure zero set of times. It's a physical phenomenon. Nobody worked on this until the 90s, when Michael Berry did the analysis for the free space Schrödinger equation, which is a second order dispersive equation, and he showed why this happens. It's not so difficult, but let me show you. This is the numerical solutions for Schrödinger. I haven't written it down. It's not like the heat equation, which is not dispersive. It has a term I in front of the second derivative to make it dispersive, but this is the free space equation. Periodic, if you start with a step function, and forget this is an approximate step function really, but if it were a step function, there would not be the vertical lines, and I will show you some more like the blue line here. Okay, that's the initial condition. And the real part of the solution is plotted at some times that are rational multiples of the period and some other generic times, and you see the same dichotomy. So it seems that, and it's very unusual to have a solution that in terms of regularity does not depend only on the regularity of the initial condition. It also depends on the particular time at which you're looking at it. Okay, so at times that are multiples of the period, you get the same regularity as the initial condition. So if you have discontinuity, you get discontinuity, and in fact, really, it really is just a sum of copies of the initial condition. But at other times, it's a completely different class. It's a continuous function, probably nowhere differentiable. It has high fractal dimension. And well, these are other computations to persuade you. Really, what you have, if you start with something like a wee box like that, thin and long, that was a sort of approximation to a delta function. Then at times, both the real and the imaginary part of the solution, there is an I, remember, even if I start with a real profile, the solution will be both real and imaginary. But both the real and the imaginary part present this phenomenon, okay? So at these times, there are just several copies rescaled of the initial condition. And at other times, it's just continuous function, very, very oscillatory. So this is now, let me encapsulate what I've said in a theorem, which is not a theorem I proved, but it's not been proven very long ago. All of this stuff has come together just around 2015, let's say. So about the time that I heard the talk, or just a little earlier. So if you start with a function that is of bounded variation, now this captures functions that are piecewise continuous, piecewise differentiable, but are allowed to have jumps. In fact, the first formula is true for any initial condition in L2. BV is particular is L2, but any initial condition in L2 satisfies this, that at this special time, the solution at time that is a rational multiple of the period, 2 pi, is just some sum with some explicit coefficient. It's a sort of Gauss sum of copies of the initial condition. U0 is the initial condition, translated. Okay, how many copies? Finitely many. How many depends on this denominator. Okay, and this is true for any L2 function. Of course, it's very obvious if you start with a step function, because then you just see step functions. If you start with something else, you might not recognize this phenomenon. But if U has this particular regularity, then at any other time, both the real and imaginary part are in fact continuous, and a bit more. If you're not regular enough, you're not even in, you're just L2 but no more. You're not in Hilbert space. Sorry. HS, I can't think of the name right now. I have a mind blank. But if you're not very regular, let's say, then from almost all values of the time, the graph of the solution has a high fractal dimension.
Sobolev?
Yes, Sobolev spaces. Yes, sorry, I couldn't come up with Sobolev. L2 base Sobolev spaces. Okay. So this is an analysis theorem if you want, but it really describes what's happening. And the interesting thing is that if you now go to the full nonlinear PDE, that's the nonlinear Schrödinger equation everywhere, very famous PDE. It's not quite the same, but there is a theorem. It's not very difficult to prove that the solution is driven by the behavior of the linear part of the solution. And so you have the same kind of dichotomy between rational times and generic times. That's true if you add also other nonlinear parts. It needs a very, very strong nonlinearity to kill this. But certainly if you take this kind of nonlinearities that comes from physical consideration, then it's not broken. So in summary, well, maybe I don't need to, I've said enough, but there are these periodic revivals that the solution of a linear dispersive periodic problem, if you look at this special value of the times, is given by a finite linear combination of copies of the initial condition. And that's very more general. I won't go into this. You don't need to have just, I gave the theorem for Schrödinger, but you can have any polynomial dispersion here. P is a polynomial. Any polynomial, it does the same. So in particular, the Stokes function, the third order one, falls into this category. And you always can write the solution as a finite sum of copies of the initial condition. So that gives the result for the very first graphs I showed. I cannot resist, giving the proof because it's so very simple. It really depends on three things. You write the Fourier series of the solution. You can do that because the problem is periodic. So e to the I kx is a basis for all level 2. So you can just express the solution in terms of this basis. Okay, and this is the Fourier series of the solution for all j in z. But now I am breaking it up in the modularity class mod q. Okay, so I put all the indices that are congruent mod q together, and then I just add all these classes from 0 to q minus 1. So I've done nothing. It's just rewriting the Fourier series. And then I remember that the nth root of unities satisfy this identity. If you sum them all, you get 1. Okay, this is a very basic identity, 1 over q. And I can put this 1 to multiply that and rewrite this red sum in a slightly different way. And then now I recognize that this is just the initial condition at different points. This is just the Fourier series of the initial condition at points x minus 2 pi k over q. And then I remember also that multiplying just by an exponential in the Fourier transform corresponds to translation, and that's what is there. So it's a very elementary proof, okay? It only uses Fourier series and roots of unity, nothing more. And if I just plot that finite sum, this is for when you zero is a step function, you get something like this. So you really see these steps. This is not an approximation. This is an exact solution. The others were approximation by truncating the Fourier series. Okay, so this is real. And at other times, it gets fractal. And this is the general result just for general polynomials. It's 3/2 for Schrödinger. We don't know exactly for Harry. It's somewhere between 5/4 and 7/4. But you can prove this as well. Okay. So why was I interested in this? I wanted to try and change the boundary conditions for the third order problem. I had worked with this, so I wanted to see what happened. So for example, take my favorite equation, Airy equation, ut equals uxxx. So Airy is ut is uxxx. This is Schrödinger. Well, the linear one, free space. So I'm looking at the third order problem, I'm changing very little. Look, it almost feels like it's almost periodic. I'm saying Dirichlet boundary condition, you're imposing that the solution is 0 at the 2 boundary points, but also that the derivatives are the same. I'm not saying anything about the second derivative. I cannot. You can only give 3 conditions because it's a third order problem. So periodic just says that both ux and uxx are the same. I'm not quite saying that. It's slightly different. And then I plot the solution. And it's something completely. There is still a difference between rational times and irrational times. So if I take a generic time, it will be these jumps create very wild oscillations. But if I take a rational time, well, I don't see jumps, but I see some funny cusps. Certainly, so this was very mysterious and very intriguing. And it took some time to unravel it, but really what is at play here is the interplay between the specific basis for this problem, and this one is not the same one as before. This boundary condition do have a basis of eigenfunctions, so there is a series solutions for this, but it's not the exponential or sine or cosine. It's more complicated, and suddenly the periodic Hilbert transform comes into play. Okay, this is the Hilbert transform, and forget about this principal value integral. So what is important is that if you take its Fourier transform, it's almost like it just changes the sign of some of the Fourier coefficients. So it leaves the part with negative Fourier coefficients alone and flips the sign of the positive one. Okay, so it's a very simple operation in spectral space. And the crucial identity that comes from this, but it's what causes those cusps, is the fact that if you just consider the sum of the positive part of the Fourier series of a function, that is given by the function. Okay, there is something about the mean of the function. If it's mean 0, this term is not there, but that's just a constant. And then it also has a complex part, even if f is real, and the complex part is given by the Hilbert transform of the function. Completely elementary, but also completely crucial, because if you take the the Hilbert transform of a step function, where there are discontinuities, the Hilbert transform has these cusps. And actually, these are infinite logarithmic cusps. They are not shown as infinite, because Mathematica cannot cope, but you should think of these as infinite. So if there is a reason that the solution of your problem only involves the positive Fourier coefficients, then immediately the Hilbert transform comes into play. And that's really what we discovered. In this problem here that I wanted to see, you cannot write down exactly the eigenvalues and eigenfunctions. You can only approximate them. But you can approximate them in a clever enough way that you can write the solution as a series involving only positive frequencies. And that's why the Hilbert transform plays a role. And the reason we understood this is that we had looked at another problem before this without understanding really things so clearly, but we had looked at this problem, which is another important dispersive equation in wave models. In fact, this is one of the equations I worked on for my PhD, though it took me ages to put 2 and 2 together. I didn't remember I'd seen this equation. I had worked on it before. So this is dispersive, but if you solve the periodic problem with a step initial condition, this is exactly what you see. And that's because there is the Hilbert transform in the equation itself. Okay, and this is really almost like Schrödinger. Schrödinger has k square in the spectral space, and Benjamin Ono, which is ut equals h uxx, has k mod k in the spectral space. So they're really quite close. But it's not a polynomial anymore, so it's not covered by the theorem, and something different happens. Okay, and what happens is that because you have the Hilbert transform, then the solution, you can relate it to the solution of Schrödinger equation, the one that we know very well from 200 years, more or less. But it has also, this prime should not be here, it has a complex part that's given by the Hilbert transform of the solution of Schrödinger. The solution of Schrödinger has jumps if you start with a step function, so the solution of BO has cusps. Okay, so the first proof that we gave of this cusp behavior was very much more involved than this. It involved special functions and sort of hands-on computation. This is work that I did with Peter Olver, and he is the son of Frank Olver, who really was the top expert on special functions in the world. So I think Peter just grew around special functions, and when we wrote an expression for the solution of this problem, he immediately saw special functions lurking in there, and we gave a really ugly proof involving special function, if you ask me, because it just relied on all these properties that you can find in the library of special functions. I didn't understand why this was happening, whereas this other proof that we gave a couple of years ago now is very clear and obvious why this happens. And once we knew this, once we knew this, we can explain why these cusps happen as they happen. And in fact, we also proved that at generic times you have the same fractal dimension. That's more surprising because this oscillation really comes when you have jumps. We weren't expecting them to be produced in quite the same way when you have instead cusps. And they're not, they are much more structured. You see, there is a sort of profile that they follow rather than a whole oscillatory mess. But so there is some self-similarity at play, and I think that possibly one needs to study a bit more closely what's going on, but we can prove that the fractal dimension overall is the same as for Schrödinger, so 3/2 for generic times. Very strange. Continuous. So at irrational times, the solution is unbounded, and at rational times, and at irrational time is continuous and bounded. Very funny. And in fact, Mignon there are subtle differences between irrational times that are based on transcendental or algebraic numbers. And well, we were on a roll at this point. So with my colleague at Heriot-Watt, Lionel Bolton, he said, oh, there is this problem. It comes from metamaterials, cloaking materials, having boundary of invisibility. But in its simplest, so they all come from some application, but its simplest manifestation of this cloaking is by taking just an interval, divide it at some point, put linear Schrodinger with plus sign on one side and minus sign on the other, the Dirichlet boundary conditions. And here, you just impose that the solution is continuous, but the derivative flips sign. Okay, and this is a very, very simple model of these cloaking effects. And we thought, so if I start with a step function or with a function that has a discontinuity, say, on this side of this point, what happens? Oops. And this is what happens. This function, this is a bit dense. So let me unravel it for you. So we start with two discontinuities on this. This is B here. So that's where there is this invisible boundary. And there are two points of discontinuity in the initial condition on the left of these invisible boundaries. And then you let time run. And you're not on 0 to pi, you are on 0b. So you have to take rational multiples, not of 2 pi, but of b squared over pi. That's just because that's easy to see from writing the Fourier series. But anyway, it's a slightly different multiplier, but it depends on the length on which you are expanding. And you see that these continuities generate, also here they generate cusps, although this is Schrodinger, for rational times and generate oscillation for other times, but they never go through these invisible boundaries. On the right, you stay nice and smooth and continuous. And if you put these continuities on this side, you see the same happens only on that side. If you put them on both, well, because the length of the interval, unless b is 1/2, the length of this interval and of this are different. So there are different rational times on the two sides, and you see the effect play on the two sides completely independently at the correct rational times. This is not so easy to prove, but we do have a proof, and it's all done in terms of spectral approximations and finding the leading order and extracting eventually a representation of the leading order that is a Fourier series only involving positive frequencies, and that's why these cusps come. And even the numerics are a little bit rough because it's very hard. You need lots and lots of terms to have a good approximation. But anyway, doing this was A, surprising, B, a lot of fun. So I feel really that I've been so lucky that I found this problem. And I now am in search, just let me give you, not in search, in discussions about applying these results to something like maybe cybersecurity or some sort of encryption systems. They are so subtle, these effects. I feel there must be, and I'm talking to a colleague in computer science who is an expert in cybersecurity, who seems to think that there may be something we can do. Anyway, so this is why I find this interesting. There are all these dichotomies at play between irrational and rational times, polynomial and non-polynomial dispersion that introduces different things. Also, and that's for application is absolutely crucial, right? Because nothing will be a perfect linear periodic problem, but this phenomenon is very robust. You put a nonlinearity, it still survives, not quite in the same exact way, but to a very, very high degree. So the solution will be a part with jumps plus some small continuous component, which really doesn't affect things much. And it also survives by perturbation to quasi-periodic problems, or if you put a stochastic noise in the boundary or in the initial condition. So it is really quite a strong, real phenomenon. And in cusp form, it appears when you have non-periodic boundary conditions. So really, there should be applications, maybe even in number theory, who knows. Okay, so for me, this has been a really fun journey, but it wasn't just me. I had lots of people that I work with, and I've divided them into 3 rough categories. The students, I've learned infinite amounts from the students because they always ask questions I don't know the answer to. And so you have to sit down and think about it with them or without them. But I find working with students really exciting. And I was really very lucky to have fantastic students. At the moment, only one of this list has not finished. Theo is finishing this year, alas. I hope he'll go away to bigger things, but if I could keep all the students with me, I would be very happy, but it's not good for them. So the students are probably the most important cohort because it's where I feel that I've given something very tangible back. And then I have mentors, which are the older or more senior colleagues that I met when I was junior and that really helped me. And I assure you that there were times when help was absolutely necessary, especially in the transition between PhD and postdoc, when I wasn't sure I could finish my PhD. Vasilis Dougalis, who died recently, and whom I met in Greece because, well, I was in Greece for, again, personal reasons. He was absolutely crucial in supporting me at the time when I wanted to quit and just stop. And he said, no, why don't you try this? And I don't know, he did it in a way that was really supportive. And, you know, we can talk all we want about the community. The people you encounter are really crucial. You know, they really are important. And then the others, in a way or another, have been important in presenting problems to me and offering to work together on them. And colleagues, well, those are the people that I've been working with more recently, where maybe I've brought the problems rather than the other way around. But this is a slightly artificial or sentimental subdivision, is not important. But I think all of them are really big debt of gratitude. So I'll finish here. I had another slide that was a bit silly, and it said that my career advice is not to be miserable. There was a picture I found online about imposter syndrome, and do we know about that? With all people looking gloomy, trying to win a race. And that's not the way to do it. It's not a race. You have to enjoy what you're doing. And we all have different speeds and different way of thinking, and all of them contribute at some point. So don't give up. Thank you.